Today's lesson is on differentiability. We're going to talk about the four instances of non-differentiability: corners, cusps, vertical asymptotes, and discontinuity. Here's your warm-up. Evaluate that piecewise function to determine differentiability. Recall, for the limit to exist, it must approach the same value from both the left and the right. I'll give you a little bit, press pause, and then I'll come back. Okay, first, in order to determine if something is differentiable, you must see if it is continuous. That's a really important part of the definition, because a lot of times what will happen is that we will determine that something has the same derivative on both sides, but it may not even match up. So if you substitute 1 into both of these parts of the piecewise function, you do get 4. So this function is continuous at 1, so that's good. Now, the other part of the definition of differentiability is not only does it have to be continuous, but the derivative has to be the same from both sides. And so if we're looking at the definition of the derivative at the point 1 in both parts A and B, what we have to see, if this is going to be differentiable, is that these are going to be equivalent. Basically, what's happening is the slope of the tangent line is the same coming from both sides. If that works, then this is differentiable. If not, then it's not. So what we do is we look at this function here and its derivative from both sides. So the limit as x approaches negative or 1 from the left of f of x would be the left side, so x squared plus 3 minus the value of the function at 1, which is 4. Since it's continuous, it works out, divided by x minus 1. So this ends up being x squared minus 1 over x minus 1. When we factor x squared minus 1 into x minus 1, x plus 1, what we're going to end up with is the limit as x approaches 1 from the left of x plus 1, that is 2. Now let's take a look at this guy on the right. So if we're evaluating as we approach 1 from the right, that means we are going to substitute that function in. The value of the function is still 4. So now the limit as x approaches 1 from the right, if we simplify the numerator, it's x squared minus 6x plus 5. We can factor the numerator into x minus 5, x minus 1. And so then the limit as x approaches 1 from the right, we can substitute 1 in and we get negative 4. So the limit as we approach from the left is 2, and the limit as we approach from the right is negative 4. That means that our derivative, or basically the slopes of our tangent lines, are not the same in both directions, and that means that this function is not continuous. So let's take a look at what the actual graph looks like. And if we take a look at what the graph looks like of this function, it's clear that it's continuous because those parts meet up at the exact same point, 1, 4. But the slopes are clearly different. That is not differentiable. We're going to call that a cusp as we move along. And cusps are not differentiable because the slopes of those tangents are, the slopes of the tangent line coming from the left and the right are very different. And therefore, we don't actually know what, like at that same point, we would have to have 2 different tangent slopes. And that's not possible. So therefore, that would be not differentiable. Let's go through our worksheet real quick. A corner is a function whose graph is otherwise smooth, but it will fail to have a derivative at a point because the one-sided derivatives differ and they are constants. So if you look at this particular problem, recall that the absolute value graph, any type of absolute value, the definition of absolute value is actually a piecewise function. So if we look at this and we actually took the derivatives, I'm not going to spend the time doing that right now using the long method. I'm just going to tell you that the derivative from the left is -3 and the derivative from the right is +3. And so what's going to happen if we look at the graph of the quote unquote tangent lines of this is that it's going to have two different horizontal lines. Uh, so if we look at the graph of the absolute value of 3x, it's a V, so you can clearly see that there's a corner. That is not continuous at the point 0. It's continuous otherwise, or it's not differentiable to point 0, my fault. Not differentiable to point 0. It's continuous everywhere. Not differentiable to point 0 because if we look at the derivative of this function, the derivative of the function does not actually have a value at the point 0. One side, it looks like it's going to 3. The other side, it looks like it's going to -3. So if our derivative graph doesn't meet up everywhere, then we cannot be continuous. I'm sorry, then we cannot be differentiable. I have to use my words a whole lot more careful. We are not differentiable at that point. A cusp. A cusp is a function whose graph is otherwise smooth, but it will fail to have a derivative at the point where the graph has secant lines approaching infinity from one side and negative infinity from the other. So what happens is this kind of looks like a corner, and it basically has the same properties as a corner when you look at the graph. So it's continuous the entire time. Like if I zoom in, there is a value at 0, 0. So it's continuous. There's no break in continuity at all. I can substitute every value of x in and it works. But if I take a look at the graph of the derivative, what's happening here is that the derivative goes off to negative infinity on one side, positive infinity on the other. It doesn't end up working out where I get one particular value for the derivative at 0. So even though this graph is continuous, once again, we have a break in differentiability at 0. A vertical tangent is a function whose graph is otherwise smooth, but it will fail to have a derivative at a point when the secant lines both approach the same value of infinity. Okay, so if I look at the graph and then I look at what the derivative slopes kind of look like, we'll take a look at how this one works. So this function looks kind of weird. It looks like it actually goes vertical at some point in time. Now, since it's a function, it never actually really goes vertical ever, except for at one possible point. So if I zoom in, it's actually never going fully vertical except for at the point 0, which sounds kind of weird that it can go vertical at exactly one point. But that's what's happening to that tangent line at 0, 0. At 0, 0, the tangent line is fully vertical. At all other points, it's really close to vertical, but not quite, as you're kind of close to that point. And then clearly it levels off as you go along. So if we take a look at the derivative of this function, the derivative of the function is always positive, and it gets really, really big, really, really fast as we approach x equals 0 from both sides. Okay, so that is why this one doesn't work in terms of differentiability. There's no actual point there for the derivative. There is a point for the function. It's still continuous, but it doesn't actually have a derivative point there. And something that's kind of interesting about this is if you take the derivative of this, like if you actually tried to do the limit as x approaches a of f of x minus f of a over x minus a, what you would find is if you took the limit from the left and the limit from the right, they'd both be infinity in this case. But what ends up happening is when you take the derivative of this function using a shortcut or something like that, or you just take the limit using this, what you're going to end up with is you're going to end up with some kind of thing where you get 1 over 0 or 3 over 0 or something like that. So it actually ends up going off to infinity on both sides. Okay, finally, a discontinuity. A discontinuity is a function whose graph is failing to have a derivative at a point because the function doesn't actually have the same value on both sides. So if we take a look at this one, we end up with on the left, it's equal to 1, and on the right, it's equal to 2. It's obviously not completely equal to 2 because it's greater than instead of greater than or equal to. But as we approach from the left, the limit of the function is 1. As we approach from the right, the limit of the function is 2. Since these two things are not equal, it doesn't even, like, it can't possibly work out, even if the derivatives are the same. And so that's kind of an important thing to make sure that we're aware of. Oops, sorry. So you can see that this function is clearly not continuous. So therefore, it cannot be differentiable, even though the derivative has a value at x equals 1. That value is 2. Both of them work out, but you cannot consider this function to be differentiable, even though the derivative has a value, because the function clearly does not meet up. And so that's something that is important that we have to be aware of. Okay, so let's review. Corner. A corner is a function that has a specific, like some kind of point in the graph, and they're both linear. A cusp has some sort of weird point where they meet up, but they're both curved going into it. A vertical tangent is a graph that actually goes vertical at one particular point, and a graph that's discontinuous is a graph that has a gap in it. Okay, I will let you do the 3 problems that are on the back. I'll pause for 5 seconds and then I will go into it. So why is this function not differentiable at x equals 0? If we remember that the definition of absolute value of x is x when x is greater than or equal to 0 and negative x when x is less than 0, then what we have is a piecewise function where the function is x plus 1 when x is greater than or equal to 0, and 3x plus 1 when x is less than 0. So even though this graph is continuous, it is not differentiable, because if you take the derivative of the top one, you would get 1. And if you take the derivative of the bottom one, you would get 3. And so what this graph is going to look like is it's going to look like something that's a lot steeper heading into this and then a lot more shallow after x equals 0. I'll show you that graph in a minute on Desmos. Second one, determine whether the function is differentiable. Oh, by the way, this is called a corner. That is a corner. So let's go into the second one. Is this graph differentiable at x equals 2? The answer is yes, and I'll show you why. First, we have to check continuity, and f of x at 2 is equal to 5 since it works in both parts of the piecewise function. It's both 5. So that is good. Now we will check the limits. So the limit as x approaches 2 from the left of this function, I'm sorry, the limit as x approaches 2 from the left of the derivative of this function looks like this. It's 4 from the left, and it's also going to be 4 from the right. So what we have is the numerator is going to turn into x squared minus 4, which factors into x plus 2, x minus 2. Those cancel, we make a substitution, and we get 4. If we look at the limit as x approaches 2 from the right, we will get of the derivative, sorry. So we get function minus 5, since both of the values of the function are 5, divided by x minus 2. The top turns into 4x minus 8. You can factor out a 4. So this ends up being 4 times x minus 2. Those cancel. This is just 4 instantly. You don't even have to substitute anything in. So clearly, the derivative is the same on both sides. The function is the same on both sides. Therefore, this is differentiable. Finally, which statement is true? Differentiability implies continuity is true, because if something is discontinuous, it cannot be differentiable. That was our fourth rule. Continuity does not imply differentiability, because we had a bunch of cases, for example, the vertical tangent, the corner, and the cusp, where the function was continuous and it was not differentiable. And the last thing I promised I would do is show you these functions on Desmos. And here they are. So this is example 1, where we have a corner at x equals 0, 1. And this is the piecewise function, which has a point 2, 5. And also, as you can see, it actually looks like the slope of that tangent line is the same at that point. And we calculated it and we showed that it was. Hopefully you learned something from this video, and I hope you have a good rest of your day.